So I'm going to actually keep it in this view because I'm going to be jumping back and forth between the editor and the presentation. But today, I'm just going to be talking this the second video in programming with CKB, and it's going to be about building dApps with a user-defined token standard on CKB. And basically, going to go over a high-level view of how do you approach applications, what are the mental models, then look at an approach to project setup, and then actually apply our mental models to building a token, and then actually build that token. And the goal of this presentation is really to answer one question, which is, I have an idea of something to build, where do I go from there? So CKB dApps, 10,000 foot view, just how to think about them. And it really, everything that I talk about today comes down to one thing, which is building correct transactions. That's CKB development in a nutshell, dApp development in a nutshell. And the basic architecture, this is similar to what was mentioned yesterday with the separation of generators and verifiers, but off-chain, you have generator logic in generators, such as wallets, maybe side chains, and apps that use the SDKs. And ultimately, they gather, package, and submit transactions to CKB network. And from there are on-chain scripts, also written by the developer, that deconstruct and verify the pieces of that transaction. So generators build and submit transactions, scripts verify transactions. And another way to think about this is that they kind of the reverses of each other. So in the off-chain generator, it's basically aggregating on-chain state and then building some, and then describing some new on-chain state that it wants to change. And it gathers all that together, and packages it into a transaction. And then this transaction is sent to the network, and the verification scripts. So once the network has a transaction, the transaction has to be verified, and this is done by the scripts attached to the cells that were packaged inside the transaction. And as you can see, it kind of from step one, all these cells get combined together into a nice transaction that gets into the network. And then those cells get pulled apart again and verified individually. And all verification scripts have to pass for the transaction to be considered valid. It's an atomic operation in that sense. And there's one big question, which is how do we model and translate application logic to CKB programming model? And in Ethereum, it makes sense. There's an API that a smart contract implements, and all you have to do is write some functions inside the smart contract, give the smart contract some internal state, and when you send the messages, and then users can send messages to the contract, and the contract reacts to them, right? The contract on Ethereum can maintain an internal state, and it can mutate that internal state, right? So smart contracts have side effects. In CKB, it's a little complicated because you can't send messages to CKB scripts. And when I say CKB scripts, that's the CKB scripts are analogous to smart contract, but I don't use the term smart contract because then that adds confusion about which system I'm talking about. Anyway, you can't call CKB scripts in that way. There's no events, there's no messages that can be passed, and there's no request response API or anything that that behaves like it. And CKB scripts also don't have side effects. So they don't update any state, they purely verify state. So how do you make a dApp and write on-chain code that changes state if CKB scripts don't have side effects? Right? And the way to think about this is that, well, in Ethereum applications, we know how this is solved because both queries and operations or state changes are mapped to function methods inside of a smart contract. In CKB, this is what the mapping looks like, is that if you're trying to support a specific query, such as get a token balance for a custom token, then what you have to define is what does the cell that stores that token data look like on chain? And then you also have to define how does the Rpc API work in order to retrieve that cell. And the Rpc API is basically just a standard API that every CKB node implements. And you can do things like get cells by lock hash, right? And so the combination of that standard API implemented by nodes plus specifying your data structures provides enough information for off-chain parties to form a query to retrieve the relevant information. And state changes are the other portion. State changes or operations, such as transfer a token, is basically a process of transaction set design. So in Ethereum, both of these types of functionality, queries and state changes, are implementing functions in a smart contract. In CKB, the state changes one is actually designing a transaction. So remember that generators package a transaction together, and then verification scripts deconstruct and validate each portion of that transaction. So they both have to follow the same rules, right? Because the goal is to build correct transactions. So the generator has to know the rules, and the verification scripts have to know the rules. And in that way, the generators build transactions that will pass verification scripts, and the verification scripts ensure that only those correct transactions pass. And we can get from this idea to this model by following this high-level modeling workflow, which is just 3 steps. 3 high-level steps is, first, if we want to build a dApp of some sort, we have to define the operations and queries that it's going to support. And then, in order to be able to handle queries and build correct transactions, we have to specify what the data structures are that will be involved in the system. And then we map the operations to transaction sets so that generators know how to package a correct transaction, and our verification scripts know how to validate that transaction and recognize it as correct. Now, this workflow is something I'm going to be coming back to over and over again over the course of the presentation. It's pretty core to this entire approach. And with that out of the way, the high-level map, we'll apply some of this to the user-defined token. And in this section, there's going to be, I'm going to be doing a lot of coding stuff as well. And so I want to just go over what the project setup looks like first. And basically, project can be split into the generator and verifier. On the generator side, we have the SDK, molecule, which is a serialization format, which I will explain later. And then On the verifier side, you have the CKB compiler, so you can compile your scripts, the standard library, and also molecule. And there's also on the generator, you notice CKB Studio, which is an IDE, and they just released support for JavaScript and debugging. I did not use it to build out the stuff I'm going to be showing today because I was doing it before they came out with that good stuff. But it's very easy to install for Mac, so make your job a lot easier. Anyway, let me just show you this project setup. So as you can see, I have this repo CKB script set up, and I have three main, besides node modules or dependencies, three main folders: generator, verifier, and shared. Inside the generator code is just an app, and I have some boilerplate stuff here which just provides convenient methods and setup. And then I have sudt.js, which is where the code is going to live that builds a transaction, builds token transactions. On the verifier side, I have the fork of this CKB miscellaneous scripts repo, which you can find on GitHub. And it's quite good because it already has some script development dependencies in there. And this repo will also be available tomorrow. And then I have shared, which is the other big one. And that's kind of, think of that as stuff that forms a bridge between the verifier and the generator. Remember, they both have to follow the same rules. Generator wants to build the correct transactions, verifier wants to ensure that those transactions are correct. And part of that is how the data is formatted. And so inside of shared is where my schema for the token data is going to live. And I'll get into the schema, which is what molecule is used for soon. All right. So we want to build token, a simple token. And the first step in the high-level modeling workflow is to define the operations and queries. And actually, we can kind of perform some developer steps in parallel with defining the operations and queries. So every time there's the model, I do the modeling step, can also go to the dev step. And so if we're on the first one, define the operations and queries, the next dev step would be define generator functions. And this workflow kind of guides the entire process, regardless of what you're building. So for SUDT, or simple user-defined token functionality, for the scope of this first presentation, there's going to be just an operation, which is issue or mint, and two queries, get balance or gather tokens. Now, I put issue and mint together there because you can think of minting as subsequent issuance, or you can think of issuance as initial minting, right? So they're pretty similar. And the properties is just there for additional understanding, is that the simple user-defined token, and which is based on the SUDT standard posted on Nervo's talk forum, defines a token that is fungible and transferable. So those are some fundamental properties about it. So if I have my operation and queries, if we go back here, now I have to define my generator functions, right? So I'm going to just go into my project, go into my generator, and define those. Sorry, these should be folded. And so I have issue UDT, which is my generator, which is the one to perform an operation. And I have these two queries here, get balance and gather UDT. And I was having perform transfer, but I'm not going to have perform transfer anymore. So that's it. All you have to do, just define these high-level functions, just their function signatures. Don't pay attention to these top two here. Just pay attention to these three. Right? That's all you need at this point. And then I have my operations and queries. That's a pretty straightforward step. And I need to now design my data structures, all right? Because that's the second step in the modeling process. And the development step there is actually defining a schema that can be used in the code. So if I have my data structures, that's good, but not enough to accomplish anything. I need to make sure that my code follows the same rules that I've already defined for my data structures. And so let's think about what a token requires on CKB. Now, I say UDT cell requirements in the slide because tokens, I mean, cells are the unit of state storage on CKB. So it's going to be defined, it's going to be stored in some sort of cell. So what are the requirements for this cell to make it a user-defined token? And basically, we need two things. The first thing we need is an amount. That's pretty fundamental to a fungible token, right? Is you need to know how much of the token there is and how much of the token a person has. And then we need a way to identify one token versus another, right? Because if we just defined an amount, then, and I create a token and you create a token, then, and they both have amounts, well, how do I know? How does my wallet, for example, know that one token is different? My token is different from your token in type, right? You need a way to define and differentiate between tokens of different types. So even if they have the same business logic, if they're basically issued by someone else, then they're a different type. And so this way of identifying and differentiating between tokens, we call it token ID. But first we'll focus on the amount one. And basically in the SUDT standard, the amount is a UN128, but that's a pretty sufficient size number for a large amount. And basically, since the cell model provides us with a data field in which to store arbitrary data, it makes a lot of sense to store the amount inside the data field as the first 16 bytes, in this case as a UN128. So we have the data field and we have amount inside of it. And that's one way to represent how many of a particular token is stored within one cell. And once again, we're in the design data structure step, and I've now designed the first data structure. So it's time to move on to the developer step of defining the schema and the logic that uses that schema, right? And this is where Molecule comes in handy. So I want to just be explicit about the problem Molecule solves before I actually use it. You can see that we have on the screen here the high-level architecture again. But on the left is this encoding column. And you can see that on the off-chain generator side, it looks like the payload submitted to the network is JSON. And that looks like hex strings, right? But when the validator scripts run, the actual scripts we're going to write to verify transactions, it's binary data. And it's interesting because basically generators and verification scripts have different views of the transactions. Even though generators are the ones building it and verifiers are the ones deconstructing and validating it, there's different, they see the data differently, basically. And since they have a different view of the transaction, since scripts have a different view of the transaction data than the generators do, and vice versa, this creates a potential problem. Say the generator submits a cell with this hex string in its data field. And now the script has to verify that the cell data is correct according to some arbitrary rules that the developer has decided to enforce. Well, and the script reads the cell data, how does it know that this hexadecimal is not supposed to represent a decimal number versus a vector, right? Because those are very different, and there's very different semantics on what the data inside each of those two types of structures could mean. Since verifiers and generators can't communicate and can't really, they can't talk back and forth to agree on some sort of communication standard or data serialization standard, needs to be a way for them to know, for verification scripts to know the meaning and structure of the raw data that it reads from transactions, and the generator has to know how to package that data so that scripts can actually access it correctly. And that is what Molecule is for. It's a serialization standard, and it's pretty useful for a couple of reasons. First, many structures are already defined. So the default data structures in molecules such as cell base or out point or block, all of those are already defined in molecule for you to easily access different parts of a transaction, except for custom parts, which you need to define yourself. And then molecule is also available in libraries to both generators and verification scripts. So molecule C for C code, which would be verification scripts, unless you're using JavaScript to develop scripts such as with the CKB Studio. And then molecule CES for JavaScript code. And basically, since both sides, the generators and the verification scripts, can use a single schema, it's very easy. It solves this problem of not knowing what the data means on either side. And molecule is also very useful because all you have to do is define the schema, and the functions are automatically generated by molecule to allow you to access and validate the custom data you define. So let's do that. Remember, we've designed the first data structure, which is the amount field for UDT amount inside of the cells data field. And so the next step is to actually define that schema in the code and then use that schema. And basically there are 3 steps to defining and using the schema. The first is, of course, to generate the schema, and then it's to use it in both the generator and verifier. And so first we're going to generate the schema, which involves on the right here, creating a schema file, compiling the schema file for the verifier, and then generating it for the generator. And you see that it's a .mol extension file, which stands for molecule. And that is where the shared will make a lot more sense. As you can see inside the schema, I have blockchain.mol file. And all of these data structures here that you see are default data structures. They're basically stuff that's included in the blockchain regardless, not custom data. And all methods to access and build and validate these types of structures already exist then. But at the bottom, you see I'm going to put UDT data. And notice that I'm defining it as a table. And tables can accept many different fields. They don't just store one thing. And the reason that I'm defining as a table as opposed to just say a uint128 is because the code that I'm going to use on both the generator and verifier side to access, validate, build, serialize and deserialize UDT data is of course going to depend on the data type that I defined in here. So if you do plan to add additional data or custom functionality, you would want to define it as a table, for example, in the beginning, so that you don't have to change up all of your generator and verification code as soon as you decide to make a modification. Those tables are highly flexible. And if this seems like a lot, like what is a table versus a vector, those types of things, there is a serialization RFC in the RFC's repo for a Nervos network on GitHub that talks about each of these data structure types. Anyway, that's the first step. Is once I have a data structure defined, the first step is defining it in my molecule file, which is inside the schema shared. And then I want to basically build that scheme. I want to generate the methods to actually make use of this schema on both the verifier and the generator sides. So I'm going to go into my CLI to do that. And I'm just going to go into my CKB script setup repository. And notice inside verifier, I told you that there's a lot of stuff already set up, and that's true. All I need to do is this project has been configured to look inside the shared schema and make use of the blockchain molecule file stored in there. So I'm just going to go in there and run this make command. And I'm using Docker because that's the way that I have the CKB compiler stored. And then, yeah, I'll wait for that to finish, I suppose. And since I did make all, it's just the simplest way. And also, but basically, it just puts files, compiles files, and puts them into the build directory there. So it's just going to build multiple different ones. So I'll make another tab. So while the schema is being generated on the verifier side, I can generate it for the schema side as well. I mean, sorry, for the, while it's being generated for the verifier side, I can do it for the generator side as well. And that's pretty simple because there's just a simple command in the package JSON called generate.js schema. So I'm just going to run that. And basically that will build, so I already have this file defined, you see, but if I delete that file, that's the file, the blockchain es.mjs is the file that's created from there, right? And so you can see the result of building it on the verifier side. I get this automatically generated file with a bunch of different methods. And if we scroll down, we can see that molecule generated these methods for me for operating on UDT data. So I can verify the UDT data, I can get the amount, and I can find out some other properties about it. And on the, so this is in C for my C scripts, which will be on-chain scripts. On the generator side, I have this huge JavaScript file with classes and functions I can use to build and verify the data with the generator as well. And as you can see down here, I have a UDT data class that was automatically generated for me and a serialized UDT data function as well. And the UDT data class will validate automatically in a constructor. And it basically will check that it's actually a uint 128. So if we go back here, that's the first step to defining using the schema is we define it and then we generate the schema so that it can be used in both the verification and generator scripts. The next step is to use the schema inside the generator, right? And remember, we're still just working on the UDT data as the amount field. So using the schema in the generator is very straightforward. And this is regardless of how complex your app becomes. It follows this general workflow that I'm going through. And basically you load in the schema that was that we just generated. You want to create some data. You want to serialize that data with the molecule schema, and you want to validate it to make sure that it's been serialized properly. And that's all you need to do on generator, regardless of what you're submitting. And I'll show you. Is if we look, I'm actually going to move some things down here so that we can just focus on one specific thing. And I'm going to put it inside the issue UDT function because that's the one that has the operation that I'm going to use. And this is what the steps look like. Is first I want to load in the schema, and I can access that with I can load in UDT data and serialize UDT data from something called CKB.molecules. That's not important how that's making its way into there. Like I said, this code will be available to you, so you can investigate if you really want to. But it's a nice API. And then I want to create the UDT data. So I know that since it's a table that I'm creating, it's basically multiple key values, and so that's going to be an object. And the UDT amount is going to be a 16-byte unsigned integer, which is, so first I'm creating a UDT amount like this on this line here. And the reason I pad this with so many zeros because I'm only trying to create 250,000. But the schema that I generated will actually enforce that it's exactly 16 bytes long, which is good because then the scripts whose view of this will be byte by byte won't have any problems with accessing data, right? Won't have any problems with alignment. So load in the schema, create the data, then I serialize the data with the molecule provided method, and then I validate that schema. And the reason I only have to instantiate with the UDT data class, the reason that's sufficient is by default, it'll run when you create new classes representing data types, molecule CES, which we're using here, will validate by default. So that's it. This is basically ready. It's for submission on blockchain. And so I've loaded it, I've created it, I've serialized it, I've validated it. I need to do this. I need to do something in the verifier as well. And remember that in the generator, we're creating data and then we're serializing it and validating it. In verification scripts, we can think of it as kind of the reverse, is we're not creating data, we're reading data, raw data, binary data. Then we're translating it into molecule and then validating it. So you think of that entire flow of how a transaction was treated at each step of the process that I mentioned earlier. Okay. So that's the generator portion, that's done. I want to go into my verifier now, and the C scripts are stored in here. So I'm going to go into SUDT, and the only thing to focus on is this right here, right now. That's all I need, is to write a verification function that verifies that the amount submitted in a UDT cell's data would be correct. And if we look back real quickly to this, we see that this type field hasn't been defined yet, but we do know that in every app, you're going to need a type. If you have data that follows specific rules, you're going to need a type field that references TypeScript. Now, on the verification side, the script that I just opened that we're going to look at is the script referenced by this type field. Okay, so that's how it's attached to the same cell that's going to be having an amount. And in that way, it's going to need to verify the amount by loading in that cell's data. Okay. So the 3 steps: load in raw data, convert to molecule, validate. So I'm loading in the raw data here. And basically, this is I'm just creating a byte array because, like I said, it's binary data. I'm using a CKB load cell data method, which is available to all verification scripts if you include the CKB syscalls header, which is why I'm suggesting working off of this repo here, is all of that stuff is already packaged together for you. And we don't have to worry about the function signature right now. But basically, this data byte array will be populated with the cell's data that we're loading in. And then we're going to convert the raw data to molecule. Molecule on the verifier side has this simple structure that we can use just to point to the raw data, and then we can call the UDT data verify, which will ensure that the data truly is that 16-byte unsigned integer. And remember, this comes from all the molecule stuff comes from the schema file generated for us automatically, this file here. And so see, I just used this method, which was automatically generated for me inside here. Okay, so we finally have a mount out of the way, and that's the first requirement, is how does a token store an amount? The second requirement is a token ID. And basically, the goal here is for every token of a specific type to possess the same type hash. And a type hash is just the hash of the subfields of the type field. These are also referred to as scripts: type field, log field, type script, log script. And so we have them have the same type hashes, and that makes it really easy to query as well, because if 2 cells have the same, if all cells that store a token of a specific type have the same type hash, then all we need to do to gather those cells of that type is to filter them by their type hash, which was very easy. And let's go through how to achieve this. First, we know that a type field needs a code hash, right? And that code hash will be a reference to the UDT code cell. Matt mentioned yesterday how these type and log fields reference executable code that will be in the type script code will be executed when this UDT cell is included as input or output to a transaction. And so the code hash here references the code within that verifier script. so UDT code cell, that will store a code hash pointing to this file here, where I just went through the using molecule to verify. And unfortunately, let's think, is that enough so that the hash of the type field is unique? Well, the answer is no, because if I use the same UDT code cell and you use the same UDT code cell, we're both building a different token. We don't want them to be in the same system, they're owned by different people. Then if all we relied on was a code hash, they would be considered the wrong UDT cell. So in a sense, they're very easily forgeable. So we need something to add uniqueness. And the other field that we can make use of to achieve this is the unique hash. I'm sorry, the args field. And we're just going to put a unique hash in there. How that is achieved is, and what that unique hash does, if it does anything, we will find out later. But at this stage in the design process, you know that you need a unique hash. That's it. Because then the combination of these two, that forms the type hash, the hash of this plus the hash of this. Well, that would be unique if this hash is actually unique, but we're going to make that assumption at this stage. And then finally, the lock field, which I'm just going to jump to immediately, is up to the holder of the UDT cell. So it provides sovereignty over ownership, classic way that assets work on CKB. So now that I have what the second part designed, which is using the script, the type script fields to implement token ID, I need to use the schema and the generator and verifier again. And I actually can skip the generate schema step, because remember how I said that molecule comes with a lot of methods built in? Well, script is one of the data structures that's already built in, and so script access methods are already built in as well. So I can already access the arguments of a script anyway. The support is out of the box. And using it in the generator is very simple. That's just a process of including a script inside of an output. So remember, once I submit the cell, I need to create an output. Well, this is the type field we were just talking about in modeling. All I really need to do is serialize that. If I expect a 32-byte value, then all I need to do is serialize it, and that's enough. Okay. And if that seems weird, everything I talk about in here is also talked about in the README of this project in more depth. But on the verifier side, I do need to do something, which is, once again, the same thing, the same 4 steps. Load the raw cell data of this time, the cell script. Up there above it was the UDT data. In here, it's the cell script. I want to turn it into a molecule script, and I want to access the arguments, right? Because it's supposed to be the first argument. And this unique hash is going to be 32 bytes. And the reason we know that is because we're using Blake2B by default in CKB projects, and that outputs a 32-byte hash value. So we know that it needs to be 32 bytes just by virtue of knowing a couple things about CKB. And don't pay attention to what's down there. This is the part that we're focusing on. And all we really need to do is check that the arguments within the script equal the hash size that we're expecting. And this is just a constant that's defined up here as 32, as you can see. And that's it. Notice that this enforces that, this doesn't enforce that the first argument has to be the hash size And then other arguments in the script can be other things. It enforces that the only thing within the arguments to this script are that single hash size. So that logic could be tweaked if you wanted to do it differently, but this is a pretty simple way to do it. So now I have the second portion of the schema loaded in both my verifier, being used in both my verifier and my generator. And let's just remember where we are. So first we define the operations and queries, which was the issue operation, issue/mint, and then we made that function inside the generator. Then we went through two data structures that we need, which is what we just finished doing. So the UDT amount and the basically a way to enforce uniqueness or token ID. Now we need to actually figure out how we're going to build a transaction and run that, right? So data structures aren't enough. We need to tie this all together with transactions because, like I said, at the end of the day, it all comes down to building correct transactions. And this is kind of a diagram of what the mint or issue transaction would look like. And you see on the input, we have something interesting where we have an input with a special type of lock that's called a governance lock in governance requirements. Now, the reason that, and then on the outputs, this arg that we've only designed as unique hash so far is actually governance script hash. Basically, it's going to be referencing this input. And why would we do that? Well, the reason is because if I, as the UDT creator, am able to sign an input, and that input has a particular, i.e. my lock script attached to it, then basically what I can do is I can make use of that to signal to the UDT validator logic that I'm the owner. If I'm the owner, then I'm allowed to create more of the token, i.e. issue or mint. And if someone doesn't have this, if someone isn't able to sign an input with the lock script that's referenced here in this args, then they can't create more tokens. In that way, you don't have people continuously inflating the supply and creating tokens whenever they want. Right? And so that's what is captured by the constraints, which are for minting and issuing, at least one input's lock matches the governance script hash, which means that the inputs lock has the inputs lock code hash plus its args hashed together equals what's placed in here. Okay. And of course, the other thing, the regular schema rule of the first 16 bytes of the UDT amount of the UDT must be the output. So if we have those two, that transaction defined, we still want to be able to build it. And on the generator side, this is simply, you want to build a transaction. Well, this is what you do, is that you build your outputs, you gather your inputs and your dependencies, you package it into a transaction, you sign it and you submit it. No matter what, no matter how complex, these are the steps that you follow. And let's look at that real quick. Remember, I'm going into my generator here inside the app, sudt.js. And let's look at these steps. So the first step is I want to build my outputs. So building my outputs involves using the molecule schema to actually serialize that data. And then I actually create an output object here and outputs have, and you can see this in the documentation, outputs are just cells. So they have capacity, they have log, they have type, and they have data. Then I want to gather the inputs and package it into a transaction. Now there's a very nice generate transaction method here that does all this for me. I can specify in here the outputs I want and any additional dependencies. And then it's all packaged into a transaction for me. All the inputs are gathered. I sign the transaction, and then I send the transaction. That's all I need for the generator. On the verifier side, it's similar, but instead of loading in inputs and building an output, I'm loading in the cells within the transaction, inputs and outputs. And for each cell, I'm checking that they're valid according to some sort of custom business logic. In this case, I'm checking if the amount of the UDT in output is larger than an input, which means that a mint or issue is occurring. And if that mint or issue is occurring, then I'm going to look for that governance lock inside the inputs. So let's look at what that looks like. And that's what this here is. Just only going to look at this. So permissions enabled is a flag. And if it's false, then I know that the outputs and inputs need to be added up, and the amount of the UDT in the input has to be greater than or equal to the amount in output. So what I'm going to do is I'm going to iterate through the inputs in this while loop, and I'm just going to load the script hash of each input with this combination here. And you don't really need to read that and understand each thing if you're not familiar with C, because you'll be able to see this repo later. And then I'm basically going to compare the the hash that I retrieved earlier inside that's passed as an argument to this script with this input script hash that I just loaded from the input. And if they're the same, then I'm going to say that permissions are enabled. And if permissions are not enabled, I'm just going to continue on with my verification logic. But if they are enabled, then I could just return success immediately, because I know that the person with permissions doesn't need to be constrained by the fact that the amount of cells of UDT in output is less than or equal to the amount in input. So that's kind of a lot of information, but if this seems overwhelming, just know that first, this approach that I just went through, you can just iterate using this approach and build up more and more sophisticated applications, first of all. And second of all, this repo that I've been using to write my code alongside will be available to use and use as a reference. And the README in that project has all the information I went through. So, there are multiple different workflows that in sub workflows we talked about, but all of that, following that workflow enables you to write code that generates correct transactions and code that verifies that transactions are correct. And the next steps we're going to be taking is, well, we're going to be circling back on this workflow over and over again because it's what we can rely on to implement logic. We're going to be applying this workflow to some more complex operations. We're going to actually design and implement a monetary policy or an economic policy on chain. And we're going to look a little bit more at security of our tokens and think about some clever ways to maybe forge a token or mint, i.e. mint or issue tokens even when you don't have permissions. We're going to look at all that in the next one. That concludes all that I have for today. Are there any questions?
Tannr, will you put the code somewhere?
Yeah, so the code, all that code, here, let me share my screen again. All of that code is going to be in this repo here. Since the code also contains some stuff that I'm using for tomorrow's presentation, I'm uploading it after tomorrow's presentation. But this is what the link will be. Yeah, so people's approach doesn't have to be like the approach that I suggest in my way of doing it, setting up a project, splitting up the verification and the generation like that, and then allowing the schema to be the common bridge between them. I really like that way of thinking about it. And this project, so the purpose of this is to prepare for the internal hackathon. And this project is one thing you could use to get started quickly. That's certainly not the only way. But I think it's a very intuitive way to organize.
Okay. So you created this the structure manually, or there's something can generate the photo structure or something?
Mm-hmm. Yeah, I just created the structure. I just created the structure manually of the verifier, generator, and shared schema.
Okay.
But you're right that it should, if it's a nice opinionated way to do things, it should be automatic at some point. All right, I think that, so there are no more questions. So I think that we'll end it for today. You can ping me later if you have any on Telegram. But other than that, I'll see you guys tomorrow morning to, take this token thing even further.
Okay, thanks, Tannr.
All right, thanks.